Welcome back, everybody, to Introductory Physics, day 15. We are going to roll through some energy example problems today to hopefully get these concepts straight in our heads, and then we'll add in some additional details about energy tomorrow. But let's go ahead and get started. Do we have any questions about gravitational potential energy yesterday that were not answered yesterday? Nope, no questions? Okay, great. Well, let's go ahead and start. So here's a question that I want you to start working through right off the bat. Give it a try. Example 5. A skateboarder coasts at 8 meters per second on flat ground, then encounters a long ramp. How high did she get on that ramp if she just coasts? So I want you to take a second, think through the setup that we would use to solve this problem. Okay, so let's see. I'm getting a couple answers here for these questions. Let's take a look. Yes, there are other external forces that are acting on this box. Friction, right? And that's, I mean, the title of this example is a pretty good clue about that. Friction as work. And will that friction provide work on the system? Yes, it will. It will change the motion of our box by slowing it down. So it's doing work on the system. Okay. Will the work from friction be positive or negative? Is there any change in gravitational potential energy to deal with? And is there any change in kinetic energy to deal with? Take a moment and think through those questions as well. Okay, so let's take a look at the answers to these questions now that you've had a moment to think about them. The work done by friction is negative. Why is the work done by friction negative? Do you remember? It goes opposite the direction to the motion. It's opposite to the movement. Yes, great job, guys. It is opposite how the object is moving. So remember, work deals with force times displacement times the cosine of our angle. And if the cosine, well, if the angle of the force and the displacement is in the same direction, then our angle between them is 0, and the cosine of 0 is 1, right? Positive 1. If they are exactly opposite each other, then the angle between them is 180 degrees, and the cosine of 180 degrees is negative 1. So the work done by friction is negative. It's taking energy out of the system, basically, if you want to think about it like that. Is there any change in gravitational potential energy to deal with? No, there's not, because the box is staying attached to the floor. It's not being lifted up into the air or anything like that. So since there's no change in height, there's no change in gravitational potential energy, which greatly simplifies the math. Is there any change in kinetic energy to deal with? Yes. How do we know that there's a change in kinetic energy? It's moving. Okay, that's true. So we know that there's kinetic energy to begin with because we know it's moving. But yeah, that's right. We know that there's change in kinetic energy because it's slowing down, right? The speed is changing, and the speed matters for kinetic energy. 1/2 mv squared, where v is speed. So the kinetic energy is going to decrease the longer it moves. Good job, Colby. Yeah, it'll decrease because the speed is decreasing. Okay, so now that we've had a chance to think through these initial questions, now we can start setting up our problem to actually solve a question about this scenario. So here's our box sliding across the floor. The initial velocity is 2 meters per second. The coefficient of friction is 0.15. And I want to know how far it slides before it stops. So I'm going to take the surface of the floor to be my 0 point because that's just the most convenient for this scenario. And then, you know, our gravitational potential energy will always be 0 because it's always sitting on the floor, which is the 0 point. So in this case, our change in energy is equal again to the other work, the work from other sources. In this case, this is the work done by friction. So we're not including applied forces at this point, and we're not thinking about air resistance specifically. We're thinking about friction, so the sliding friction. So again, our change in energy is the final energy minus initial energy. And like I just mentioned, work is force times displacement times the cosine of the angle between force and displacement. And in this case, the force is friction. Why are we not considering the work done by gravity and the normal force in this case? Any ideas? Because it's moving horizontal. Colby, yeah, they don't affect its movement. Exactly, they equal 0 because the cosine of 90 degrees, they're perpendicular to the movement. So the cosine of 90 degrees is 0. They are not affecting its motion at all. Absolutely right. Great job, guys. So, like we said, there's no gravitational potential energy because it's staying on the floor the whole time. So we're not even going to bother writing that into our equation because it's 0. It doesn't matter. But we do have kinetic energy. So our final kinetic energy minus our initial kinetic energy is the change in our energy in this case. And the force of friction, we remember from last week, is mu, the coefficient of friction, times the normal force. So that's what we're substituting in for the force of friction, times our displacement, which we don't know, times the cosine of our angle. Okay, so our final kinetic energy is 0 because it's slowing down to a stop. So its velocity at that point would be 0. Our initial kinetic energy, we don't know yet because we haven't plugged in the numbers. But we can see from this equation then, the cosine of 180 degrees is -1. So that's where we get this negative out in front of mu n d. And I'm using n here to symbolize normal force. So now that we have this nice simplified equation, we'll plug in the actual equations for those things. So we can plug and chug and get our answer. So kinetic energy is 1/2 mv squared. Mu, normal force, is equal to the force of gravity. So that's mass times g. And then we bring down our displacement. And we have a mass on both sides of the equation in this case. So we can cancel them out, not even have to worry about that. And then when we rearrange that equation to solve for displacement, we get v squared over 2 mu g. When we plug in all of our numbers, we get a displacement of 1.36 meters. Woohoo! Any questions about this example? Where did the n come from? The n is normal force. Remember, we can either write it as F sub n or just n. So for the sake of space, I just wrote it as capital N. But that's just how we calculate the force of friction. So mu times the normal force is what we plugged in, we substituted it for the force of friction up in this, up in this equation. Force of friction equals mu times the normal force. that help, Colby? Yeah, great. Awesome. Any other questions? Nope. Okay, great. Let's continue. Example 7. This is kind of an Atwood machine example, except this time I'm not really super interested in forces. We saw an Atwood's machine last week when we were dealing with Newton's second law. But this time we're dealing with energy, and we can do it the same, not the same way, because we're using energy this time. But we can use different techniques for the same type of scenario. Anyway, a box of gravel with a mass of 130 kilograms slides on a rough surface, being pulled by a bucket of concrete with a mass of 65 kilograms. Find the speed of the box of gravel after it has moved 2 meters. The system starts at rest. Okay, so there are a couple key bits of information in this scenario that we should pull out that will really help us simplify the math. One, the system starts at rest. So that means its initial velocity is 0 for both objects, because if the system is starting at rest, then both of them are starting at rest. And we know that they're both connected to the same rope. So last week when we were thinking about forces, connected to the same rope meant that the tension force was the same for both free body diagrams. And in this case, it's the same rope, so that means if one of the buckets is moving by 2 meters, then both of them are moving by 2 meters, because the string is not going to stretch or compress between them. So if one moves a certain distance, the other one is going to move that same distance. And we also know that they're moving the same speed then, because again, this rope is not going to stretch or compress or get all bunched up or anything like that. So they're moving the same distance and the same speed because they're attached to the same rope. So those are some of the things that you'll want to take note of when you solve problems like this. They're not explicitly stated to you as numbers. So make sure that you put on your thinking hats or something to just take note of those clues that are kind of hidden in the scenario. So in this example, this one is a little bit more difficult than the ones that we've seen previously because it has 2 different objects in it. And we have to think about both of those objects. We can't just look at one or the other, we have to look at both. Just like we had to look at both objects when we were doing it using forces and free body diagrams. So just for the sake of helping us visualize this in the math, which is going to get a little bit crazy, I have everything referring to the box in orange and everything referring to the bucket of concrete in red in the equations so that you can see where each piece is coming from. Hopefully that helps. Okay, so once again, the change in energy is the work due to other forces. We're not considering gravity and the normal force on the box because they are not in the direction of motion. So they don't really matter to us. But friction is parallel to the motion. It's in the opposite direction. So that other that we're referring to is again friction. But this time our change in energy is the total energy. So that's the change in energy from the box and the change in energy from the concrete. So in this case, the subscripts 1 and 2 refer to object 1 and object 2, not initial and final like we've seen in the past. And that was a little bit confusing when I was going through this example, which is why I did them in colors as well. Okay, so the change in our energy for the box is the change in kinetic energy plus the change in gravitational potential energy. And then likewise, the change in energy for the concrete bucket is change in kinetic plus change in potential, and all of that equals our work due to friction. But we know that this box is sitting on the surface the whole time, and so our change in gravitational potential energy is 0 because it's not changing its height at all. And we know that this bucket, we know that the box of gravel is moving through a distance of 2 meters, which means the bucket of concrete is also moving through a distance of 2 meters. So our change in height there is -2 meters. I'm choosing the surface of the table to be my 0 point. So it's falling down a distance of 2 meters. So change in distance, change in height of -2 meters. Okay. So now we can plug in the things that we know. Our change in kinetic energy for our box is final minus initial. Our change in kinetic energy for the bucket is final minus initial. Our change in gravitational potential energy for the bucket is final minus initial. But some of those things are going to disappear because we know the system starts at rest. So the initial kinetic energy for both the box and the bucket of concrete is 0. Those are going to go away. We also know that this bucket, if it's falling through a distance of 2 meters, that means it's starting up at the 0 point. So its initial gravitational potential energy is 0. So now our equation gets a little bit simpler, but we'll go ahead and plug in our equations for kinetic energy and potential energy. So for the first object, the box, our kinetic energy is 1/2 m1 times v1 final squared. Our final kinetic energy for the bucket is 1/2 m2 v2 final squared. And then our final gravitational potential energy for the bucket is mass 2 times g times its final height. Okay. So remember that these two objects are moving at the same speed. So our final velocity for the first object is the same as the final velocity for the second object. So I'm just going to call that final velocity. And the work due to friction, like we saw in the last example, is mu times the normal force, that's the force of friction, times the displacement, times the cosine of our angle, 180 degrees. So plugging in our numbers, mass 1 is 130 kilograms, mass 2 is 65 kilograms, our y2 final is -2 meters because it's falling down 2 meters. And we're looking for this final velocity. So once we do all of that, typing in our calculators, hopefully we type things in correctly. That's always helpful. We get a final velocity of 1.62 meters per second. And that is true of both objects. Okay. So do you guys have any questions, comments about this particular example? It has moved. Oh, I love it. That was great. That was a really good pun. That makes me so happy. Making puns over text is tough. I appreciate the struggle. Okay, so this was a fairly complicated example just because we had the two objects, and so we had so many terms that we had to consider. But it was really helpful, and we were able to cancel out a lot of things once we realized those couple clues that were given to us in the scenario. So remembering that at rest means the initial velocity is 0, which means the initial kinetic energy is 0. Both of them are moving the same distance and same speed because they're attached to the same rope. And this box is staying at the same horizontal level, so its potential energy is 0 the whole time. So question, for this problem, when I originally imagined it, the box was being pulled to the left, so the height for you is +2. Does that matter? Um, so thinking about energy terms, no, that doesn't necessarily matter, um, but that's not quite a correct way to think about it because there's no force that's actually pulling that box to the left. There's no applied force in this scenario. Um, and so the box is going to tend to go to the right, downward, well, not downward, but the concrete is going to go down instead of up. So the box is going to go right instead of left. Now, if you had chosen the height where the concrete ends up to be 0, then your initial height for the concrete would be +2. And so that's how that +2 could play in, but not so much because it's pulling to the left. Does that make sense? Yes. Okay, great. Okay. So here is a roller coaster, and I want you guys to think about this roller coaster. We're going to assume that this cart starts with a speed of 2 meters per second, and I want you to put the locations in order of lowest speed to highest speed, and I'll give you a moment to think about this. Okay, so let's think about this. Remember, we're going to be thinking about energy here. So basically, this question is asking, where does it have the lowest kinetic energy and the highest kinetic energy? So it's going to be moving the fastest where it has the most kinetic energy. And that would be, if you've ever ridden a roller coaster, you probably know that you feel like you're going the fastest when you're down at like the bottom of a hill versus when you're kind of cresting the top of the hill. So use your own experience as a guide in this. We're going to be moving the slowest here at A, and then it's going to go whoosh down the hill, and then slow down even more at D. It's going to whoosh down that hill, and then it'll feel like when you're at the top of this loop here, it feels like you're moving super slow before you whoosh back down. So we're moving the slowest at A and the fastest down here at the bottom of this loop at E. So A, D, B, C, E. Interesting. So now put the locations in order of lowest potential energy to highest potential energy. Take a minute and think through that. Okay, so now thinking about potential energy, we're going to have the lowest potential energy where we are the lowest height. Because remember, potential energy is mass times g times height. So that means we have the lowest potential energy at E and the highest potential energy at A. That's where we have the highest potential to fall. So E, C, B, D, A goes in order of lowest height to highest height. And you might have noticed, if you are very observant, that that is exactly opposite our answer to the previous question of where it's moving the slowest, the fastest. And that's because of the law of conservation of energy, right? Our energy total amount is going to stay the same the whole time. So we don't ever lose energy, it just changes from one form to another. So if we have really high potential energy and then it starts falling down, well, now it's losing potential energy by gaining kinetic energy. And vice versa. If it's going really fast at the bottom of a hill and it's moving upward, then we're gaining potential energy, but then we're losing kinetic energy because it's slowing down. So these two questions are basically just opposites of each other. I don't know if you guys caught that. But now we're going to do some calculations about this scenario. So we're going to assume, again, the cart starts at 2 meters per second. The mass of the cart is 350 kilograms. We want to find the speed at each point, which you are fully capable of doing at this point. But then I also want to show you how to find the normal force at point B, which is not something that we have done yet necessarily. So I'm going to introduce these two equations to you, which deal with rotational motion. And I know we haven't talked about rotational motion yet, but we will next week. So I wanted to introduce these to you really quickly. Anyway, let's find the speed at each point. We should know the speed at A. What is the speed at point A? Good, Kobe. Yes, 2 meters per second. Right, that's like just literally given to us in the scenario. It starts at 2 meters per second. So right here where it's starting, the speed is 2 meters per second. So I want you to take a moment and try to find how fast it's moving at point D. Our initial height at point A is 25 meters. Our final height at point D is 16 meters because we have 12 plus 4. So our height here is 16 meters. Our change in energy is work due to other things. And in this case, we're not really dealing with friction. So that would be 0. There's no other applied forces, air resistance, anything like that. So that means that our initial energy, our initial total energy, equals our final total energy. So see if that hint gives you enough to get going. And if not, I'll give you another hint in just a minute. All right, next hint in case you need it. Remember, E stands for total energy. So that's the initial kinetic energy plus our initial potential energy equals our final kinetic energy plus our final potential energy. Okay, so hopefully you had enough time to at least give this a try and get to some answer. We'll see if you came to the correct answer. Hopefully you did. So our equation for kinetic energy is 1/2 mv squared, and our equation for gravitational potential energy is mgh or mgy. So we have the initial stuff and the final stuff on either side of the equal sign, but we can see that we have a mass present in all of the terms. Now, previously I have just gone ahead and canceled out the masses. In this case, I'm leaving them in there just so you can see what it looks like if you forget to cross them out. But just notice that you could, if you wanted to, you could factor all of those out. So all we really have left to do at this point is like plug in our numbers. So let's do it. 1/2 times the mass, which is 350 kilograms, times our initial velocity, 2 meters per second, squared, plus mass, 350, times g, 9.8, times height, 25, equals 1/2 mass, 350, times v final squared. We don't know what v final is. And then we know our final height is 16 meters. So lots of number typing into your calculator. Don't forget to take the square root of your velocity, and you should get a final velocity of 13.4 meters per second. Again, I didn't show all of the simplification, all of the algebra stuff, going from like our plugging in of our numbers to our final answer, just for the sake of space and making it look less cluttered. But How'd you guys do? Did you get to your correct answer? Did we remember to take the square root of v squared to get our final velocity? I'd say that's one of the most common things that students miss, is remembering that velocity is squared. So don't forget about that. Okay, so let's just like think through this and see if this answer seems reasonable. We know that we're moving initially at 2 meters per second. So by the time we get to the top of our next hill at point D, we're going to be moving faster than we were at the beginning, but it's not going to be like supersonic speed or anything like that. So like let's see, what answer do we get if we forget to take the square root? I don't even remember. 13.4 squared. You'd get 180 meters per second. So just think about that for a second. A meter, if you are more used to American, like English units, a meter is approximately a yard, which is about 3 feet. So if you're moving 180 of those every second, that is a pretty fast roller coaster. And so that answer should just make you kind of question your process. So that would be a good clue as to whether or not you remembered to take the square root. If you're getting this like hundreds answer, then you probably made a mistake somewhere. So use those sorts of things to help you see if your answer is valid. I'm glad you see what you got wrong if you got the answer wrong. Yeah, essentially you're flying at that point. You would, yeah, basically you would die on that roller coaster if you were going 180 meters per second. That'd be rough. That'd be real rough. Okay, but it does ask us to find the speed at each point, not just at point D. So let's take a look then at point B. And I'm just gonna, for the sake of time, I'm not gonna make you go through all of the steps for all of these, because really not much changes from point D to point B except the height that it's at. Now, instead of being at a height of 16 meters, we're at a height of 12 meters. So I just took point A to be our initial point again, because we know for sure what the speed it is at point A. You could take D to be your initial point if you want to, but you have to be really confident in your speed answer at point D in order to do that. And if you're not super confident, or if you got the wrong answer for the speed at point D, then you would get an incorrect answer for your speed at point B if you used D instead of A. So that's why I'm going to continue to use A as our reference point. Anyway, the whole setup is the same. So all of those equations, I just put those in there again. But the only thing that's changing in here is our final height. Right now, our final height is 12 meters instead of 16. So all of those numbers are the same, except that very last one. We changed it from 16 to 12. So take a moment, type this into your calculator. What do you get as your final velocity? Okay. So once we type all of this into our calculator, which I know is super tedious and really annoying to do, we get a final velocity of 16.1 meters per second. Woohoo! So let's think about this. Does that make sense? Well, thinking through those questions, those initial questions about this scenario that I asked before we started all of this number stuff, where it has the lowest speed and where it has the highest speed. We said it has the lowest speed at A and the highest speed at E. So A, D, B, C, E. So as we go through these points, it should be moving faster at point B than it was at point D, than it was at point A, because that kinetic energy, well, that potential energy is changing into kinetic energy. So we do expect a velocity that's higher than the previous two velocities, and that's what we get. But again, it's not in the hundreds, it's just slightly larger. So that makes sense. Okay, so now if we want to find the speed at point C, it's the same setup, except now our final height here is 3 meters. So again, same setup. The only thing that's changing is our final height, and that's 3. So again, all of these numbers are the same except this very last one. Our final height is 3. So I'll save you the agony of typing all of this back into your calculator again. Our velocity at this point is 20.9 meters per second. And again, that makes sense because it's moving faster. More of that potential energy has been converted to kinetic energy. So it's moving faster, but not hundreds faster. And then lastly, what is the speed at point E? Well, now our height is 0. We're pretty much at the ground level at point E. So our setup of the problem is the same. All of our numbers are the same except that last one, which is 0. And that does actually simplify the math for you. Yay! So we get a velocity or a speed at this point of 22.2 meters per second. And that should make sense as well because the speed at point C, which was just a little bit higher than point E, was just a little bit lower, 20.9 as opposed to 22.2. Cool. So do you guys have any questions about this part of the problem? Remember, there is another part that we'll do in just a moment, but any questions about this part of the problem? Okay, I'm seeing some all goods. Good. Okay, yeah, so this was mostly just an exercise. Eventually, it was just an exercise of how well you can type things into your calculator. But all of this physics stuff happened in the setup of this problem. So I would recommend that if you weren't really sure how to start with this, that you take a look at some of the things that I posted on Canvas. Yesterday I did go and post a uh, conservation of energy worksheet that has some problems like this to think through. So I would recommend that you check that out. Of course, we'll do some more examples tomorrow, but practice on your own time is also very helpful. Okay, the second part of this problem was to find the normal force at point B. So that would be when you're upside down in the loop here. So just to recap, we found the speed at point B to be 16.1 meters per second. Okay, so since we're asking about a force, we're going to want to draw a free body diagram just to see what the forces are even doing in this situation. So here's our roller coaster car. Of course, we know we have the force of gravity pulling down. What direction is the normal force pointing in this moment? What direction is the normal force at point B? It's kind of an interesting thing to think about. Remember, normal means perpendicular to the surface. And in this case, the normal force is also down. I know we haven't really seen an example so far where the normal force is pointed down. But remember, like this vertical wall right here next to me, if I push on this wall, the normal force is not upwards. The normal force is outwards towards me, supporting my hand. And in the case of the roller coaster car at point B, the rails supporting the car are downward, like it's supporting it downward, which is just kind of really strange to think about. But if you like take your finger and trace the normal force at each part of the loop, so at point E, clearly the normal force would be upward because the cart is down there at the bottom of the loop. And then as you go around the loop, I can't even move my arm like that, but the normal force remains perpendicular to the surface of the loop. And when you're right at the top there, it would be pointing down. Weird, I know. Okay, so like I said, we'll talk more about circular motion next week, but I wanted to introduce this to you because I think it's an interesting part of the problem to consider. So I gave you those couple equations a couple of slides ago, but our acceleration sub c means centripetal acceleration, which is basically the acceleration towards the center of a circle or due to rotational motion. And that acceleration equation is v squared over r, where r is the radius of the circle. So we know that the velocity at point B is 16.1 meters per second, so we square that. The whole loop, the height of it is 12 meters, so that means the radius is 6 meters. And that gives us an acceleration of 43.2 meters per second squared, which is pretty significant. So let me just take a moment with my calculator here and figure out how many G's this would be, because I don't do math very well in my head. So that would be 4.4 G's, 4.4 times the force, well, the acceleration of gravity. So that's pretty significant. And if you've ever been on a roller coaster like this, you probably remember the feeling of being upside down in a loop like that. It's pretty crazy. Anyway, we also know, thanks to Newton's second law, that the net force on something is mass times its acceleration. And that equation is equally valid whether we're talking about linear motion or rotational motion. So our net force, in this case centripetal, due to rotational things, is mass times our centripetal acceleration. And our net force, I'm going to take down to be positive, just because I don't feel like dealing with negatives right now. So our down y direction is positive. So we have the normal force plus the force of gravity equals our mass times our acceleration, which means our normal force is ma minus the force of gravity, mg. So our mass is 350 kilograms. Our centripetal acceleration is 43.2. Again, our mass is 350 kilograms, and our g is 9.8. So that gives us a normal force of 11,690 newtons. That's crazy. That's a lot of force. Yeah. Okay, so I know that was an example doing something that we've never done before, but it's not that far off of what we've done before. It was just really that first equation for the centripetal acceleration that we haven't done together. But that whole idea of finding the force from an acceleration, we've done that. We did that last week. So that's why I wanted to include this as an example. But do you guys have any questions, comments, concerns about this example? Like I said, we'll do more rotational motion stuff next week, but I wanted to show you, just to introduce it. Okay. I think this is the last example that I have for you. Yeah. So any questions about energy thus far? We'll do more examples tomorrow. We'll add a couple last details about energy tomorrow. And then next week, we'll be moving on from energy to other stuff. But any last questions? All right. Well, if you don't have any questions, then I hope you guys have a beautiful day. I will see you tomorrow.